Shall we do another example? Why not? We've been working with the direct comparison test, which is, it's not as easy as p-series or geometric series, but it's not bad. It's not terrible. Okay, so remember what we do first is make sure your screen zooms in or out or whatever. Positive. Are these things positive? Yeah, they're totally positive. Positive. What about the nth term? Well, if this thing is going to get bigger and bigger and bigger, these things are always positive. That stays 1. That's going to shoot off to 0. Or shoot down to 0. I don't know. Whatever. The nth term is getting closer and closer to 0. All right. Well, that wasn't very helpful. Okay. So now if I take the dominant terms here, it looks like I got 1 over n. So it looks like maybe what I'm going to converge this to, how about compare this to, is the series n equals 1 to infinity of 1 over n. Hey, what's that? That one's famous. This one is the divergent harmonic. And you know what? I'm not sure if I made mention of this 100 times. If you just mention this and this, you don't have to establish that. That's a known thing. Okay, so just have it memorized. Harmonic series, it just diverges. And if it diverges, we need to be bigger than that, right? Okay, so then we need to establish, oh, wait, let's put the word bigger. Okay, we need to say that 1 over n is going to be less than or equal to 1 over 3n plus 2. I got a bad feeling about this. You know why? That's because this is a bigger denominator than this one. We divide by a bigger number. Overall, this fraction is going to be smaller than that one. Don't believe me? Here, let me cross multiply that thing then. That was supposed to be an arrow. I don't know what this little extra thing is. Okay, yeah, I got rid of it. Pretend like it never happened. So cross multiplying, you get 3n plus 2 is less than or equal to n. No? Is that not doing it for you? Okay, so I don't know. Maybe I subtract over the n, 2n. Subtract over the 2 is less than or equal to a negative 2. Is that not doing it for you? Here, let's divide by 2. N is less than or equal to negative 1. No, it's not. It's supposed to be greater than or equal to positive 1, so that didn't work. So I was not able to establish the inequality like that. All right, well, let's go back. We've had to do this. We had to do this with another one of these. Maybe we put the 3 there. If we put the 3 here, we can pull this 3 out, and you're now 3 times infinity, which is still infinity. It still diverges, right? So I'll throw the 3 in here. And then cross multiply, again, I would have 3n plus 2, which is less than or equal to 3n, which is not, right? Cancel these things out. And we've got 2 is less than or equal to 0, which is untrue, usually. Boop. So what does that mean? It means that you cannot use the direct comparison test, unfortunately. Does that mean that this one converges then? No, not necessarily. You can still be smaller than a divergent series and still diverge. You just can't establish it with the direct comparison test. What we need is another test, and that one is going to be the limit comparison test. All right, here is the way the limit comparison test goes. So we still need to find a test to compare ours to that we know either converges or diverges. Here's the setup. Suppose a sub n is greater than 0 and b sub n is greater than 0. So basically we have positive terms once again. And the limit as n approaches infinity of the ratio a sub n over b sub n is equal to L, which is greater than 0. In other words, this limit is finite and positive, and that's usually what I'll write, is that it's finite. It is some real number that is positive. Then the two series, a sub n and b sub n, either both converge or both diverge. And there's a little asterisk there, and it basically says you still don't know what it converges to necessarily, just that they do the same thing. So why is that? Why does that work? The reason why that works is because when you're taking ratios of each of these terms, and it approaches some finite number, you're basically showing that they're ultimately becoming constant multiples of each other. Here, let me talk about this right here. Did I add an extra page? I already did. So let's say that the limit as n goes to infinity of a sub n over b sub n is equal to 3. This means that ultimately these terms are 3 times bigger, like as we get closer and closer to infinity, than the terms in the b sub n series. Like when I take the quotient, I'm getting approximately 3 or getting closer and closer to 3. And so then let's say that the b sub n series, b sub n is equal to, I don't know, maybe it just converges to 2. And the terms in this series are approximately 3 times bigger than those ones, so 3 times 2 is 5, it still converges. Or let's say that, again, come on, stop writing with a laser. B sub n is equal to infinity, so it diverges. So then let's say that this terms of this a sub n are approaching 3 times bigger than the terms in b sub n, so therefore you're 3 times bigger than infinity, you're still going to diverge. So there is the basis for this thing that we're calling the limit comparison test. So again, we still need to find a series to compare it to favorably, whether it converges or diverges. So let's try that here on example 6, which is basically the previous example that we couldn't establish with a direct comparison test. So we still wanted to compare this to, and you need to write this thing out, you still want to compare it to the divergent harmonic series, n equals 1 to infinity 1 over n, which is divergence harmonic. I capitalized it this time, series. I think that's proper. Yeah, you're going to get counted off for capitalization on the test, so be careful. All right, anyway, so then I'm going to take, I don't have to go, let's add an extra page in here. Add page. I do not have to establish an inequality. I just need to make sure that these terms are positive, which they are. Those terms are positive, which they are. I declare this one as being divergent, and then I'm going to take the limit, okay? So I'm going to go the limit as n goes to infinity. I want mine on top, 1 over 3n plus 2 divided by 1 over n, and we have ourselves complex fraction. We're just going to resolve this by, back in, what grade do you learn to divide by fractions? I don't know, but it's division by fractions is really multiplying by the reciprocal. So I am going to rewrite this as the limit as n goes to infinity. I know that looks like an h here. I'll fix that for you. 1 over 3n plus 2 times, take the reciprocal, n over 1. And obviously that one just puts the n up top here. N goes to infinity. N over 3n plus 2. Okay, and then you can use L'Hopital's rule here, or I can use a pre-cal rule. Our degrees are the same, so it should be just the ratio of the leading coefficients, which is equal to 1/3 relative growth rates, basically, which is finite and positive. All right, so it's equal to 1/3. In other words, the terms in my sequence are 1/3 as big as the terms of this one. This one goes off to infinity. If you're 1/3 times infinity, you're still infinitely big. So therefore, you must also diverge. So let's say that we're going to write up the conclusion for this one. So again, if I come back up over here, we can see that we have to establish this, right? And then we can draw our proper words are hard today. Proper conclusion by the limit comparison test. So we need to say since a sub n is the 1 over 3 n plus 2 is greater than 0, and 1 over n is greater than 0, for n is greater than or equal to 1, and the limit as n goes to infinity of 1 over 3 n plus 2 over 1 over n is equal, is equal to 1/3, which is finite and positive. Why is there a big space between the w and the h? Which is finite and positive. Then I'm going to say that our series, the limit from n equals 1 to infinity 1 over 3 sub n diverges since n equals 1 to infinity, that's an infinity symbol, 1 over n, is the divergent harmonic series. Yeah, so did you know that you were going to have to write an essay? Oh my God, really? On the AP Calculus exam? Yeah, you pretty much do. And notice I didn't even write by the limit comparison test. Man, I've already written like a full paragraph, so I'm pretty much good with that. Okay, so again, here's just a recap of what happened here back on the slideshow, where limit comparison test, we're comparing that to the convergent harmonic series right here. And convergent harmonic, did I just say that? Divergent, I'm glad it said that right here so I could read it off because I totally forgot. Hopefully you don't. And then you establish your limit here, blah, 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 which is finite and positive. And then you can say that they both do exactly the same thing by the limit comparison test.